Good day. We would like to introduce our work, Intellectualization Method and Model of Complex Technical System Failure Risks Estimation and Prediction, made specially for Computer Modeling and Intelligent Systems Conference Workshop. Problem Statement and Relevance. The diversity of compositions and the increase of the number of complex technical systems, for example, installed in ships and different other transport systems, and transport vessels is accompanied by an increase in the failure rate of such systems. This leads to the need to repair CTC equipment, which means to ship downtime and as a result losses associated with the time spent on repairs and the resources used increase significantly. The use of intelligent systems for assessing and predicting the technical condition (TC) of complex technical systems can significantly extend the life cycle of the CTS, including ships. Currently, the volume of implementation of automation, digitalization, and artificial intelligence techniques and technologies in various industries continues to grow. So, intellectualization of estimation and prediction in complex technical systems failure risks is a task related to the development of the methods and technologies that allows us automatically determining the risk or probability of failures in complex technical systems and predict their possible consequences. When we made a literature review, we would like to state that assessing and prediction the risk of complex technical system failures is a task, such as a lot of authors of modern states in this field have opinions that it requires the ability to process large amounts of data, analyze them, and find patterns and relationships between various system operation parameters. In this case, the use of intelligent technologies can greatly simplify and speed up the process of data analysis. The conceptual basis of the intellectualization of the solution of interrelated problems of complex technical system technical conditions, diagnostics, and predictions are traditional for the class of unstructured and poor formalized different tasks. The removal of the listed uncertainties and different poor worked fields can be based on solving of the problem of assessing the risk of complex technical system failures and its predictions with relative insensitivity of incomplete data on systems. There are various algorithms, models, and methods for the prediction technical condition of CTS. AI models are actively developing, in particular natural networks. But as we can see in works of different authors of our in our field, the main problem for the productive operation of natural networks is need for significant amount of statistical data, which is difficult to obtain in real conditions due to the number of reasons. For example, high cost of the system, understudy, and high cost of testing, limited time, so on. The purpose of our work is to ensure the reliability and safety of work, as well as reducing the risk of complex technical system failures by solving causes determining problem of their failures. Formation of principles for the constructing and intelligent system operations for assessing and predicting the risk of complex technical system failures with different performance. Their constituent of ages and links, and development intellectualization method and model for the technical condition estimation and prediction of complex technical system failure risks. When we're talking about our method, we would like to discover how it works. The first step in most compression methods involves changing the color model. Currently, various color models are used, and our method is based on the formalizing generalization intellectualization model of technical condition failure risk estimation and prediction of complex systems by diagnostic features, which can be described as the following form. As we can see, there are 6 different indicators which are described and the lower part of this list, such a set of FE, a complex technical system, FI, diagnostic failure risk assessments, a cyclic directed graph, a mapping relationships between sets, and failure trees. When we made a method, we would like to build a Bayesian believer network, which is our main model. It can be made in such steps. First step is the building of BBN, and the second step is the BBN parameter specifying. So in first step, we try to make verticals and intersystems or intercomponent Bayesian networks denote subsystems according to their technical condition, such as 2 points. First one, each subsystem component can be in the following technical condition, or it might be operational state subsystem component level, or it might be failure, partial, complete subsystem component level. And the last one of the first step of building BBN is the connection between the nodes of the Bayesian network are indicated, denoting subsystems, intersystems, complex technical system connections, and diagnostic appropriate assessment risk R. And the second step is BBN parameters are specified. We need to specify initial failure risks for FE and FI, assuming they are operational or inoperable before complex technical system starts. Next one, third step, is the risk of failure estimation. And the last 2 steps, we made a estimation of FE and FI, complex technical system failure risk, at the current moment of time while they are in a working state, and the current moment of time which also they are operable at the previous moment of time. So the next moment and the previous moment. Next step, we made experimental research, and this slide we can see symbols and subsystems component of our system, which we discovered. It's a ship's plane, and we used our model and method to estimate subsystem component weights and risks. We can see that we have 17 different subsystem elements, components, and there are systems, symbols, and their values of weight. On this slide, we can see our bias diagnostic model of technical condition using our BBN model, which we were built in Genie environment. From the given a priori and a posteriori data based on our system study, results included the multi-level structure of our system for about 20,000 hours of operation for a conditionally accepted system failure risk value from 0.26 and possible failures of different components such as IE, CAS, and interconnections. Lately, we made experiment results building graph, such as we can see on the slide. R is a risk and T as a time. It's a number of our scenario between 20,000 scenarios, and a posteriori and a priori estimates of the risk of our system for the input component failure risk of our ESC with weight 0.26. As a result, we can say that similarly from a retrospective results analyzing obtained by a modeling of our system, all of our elements were identified that affects the overall system performance in different ways. From the research results as reflected in the diagnostical model, it follows that the maximum non-operation state during the operation of our system, about 20,000 hours, corresponds to the one subsystem is a CSPSC subsystem directly. Since this subsystem is dependent in the level of our system layered structure, when it's in failure, it's necessary to check the subsystem in order to find its failure cause in different levels. The implementation of the intellectualization method and model for estimation and prediction CTS failures risk in the conducted studies, carried out by modeling an a priori and a posteriori data, determines our subsystems that have the greatest impact of the performance of the main engine of our system and the operation of the entire system at various points in time. Carrying out studies of emergency situation, analyzing of incidents in the complex technical system will determine the causes of the accident happens. So, based on the intellectualization of our complex technical system technical condition estimation by diagnostic features, it's possible to substate the failure risk prediction with a large number of variable parameters and with different operability. As a conclusion, we can say that intellectualization of the complex technical system technical condition, assessment by diagnostic features, the failure risk prediction values in subsystems or components or intercomponent connections of systems with different operability and incomplete data are substained. In order to ensure the reliability and safety of work as well as reduce failure risk of complex technical systems, the following tasks were solved, such as determining the causes of their failures and formation of principles for the construction and operation of the intelligent system for assessing and prediction complex technical system risk failures with different performance. This constituent FE and FI subsystem. According to our researchers, it's might be interested to follow our ideas and scientific model and method in future to obtain the efficiency and the performance of our development. Thank you for attention.